Welcome and thank you all for holding. All lines will be on a listen-only mode throughout today's conference. I would like to remind all parties that today's conference is being recorded. If you have questions, disconnect at this time. Thank you. At this point, you may begin.
Welcome, everyone. I apologize for the brief delay here. This is the first webinar of an ongoing quarterly webinar series developed as part of IEA WREN Task 34, also known as WREN, that's W-R-E-N, working together to resolve environmental effects of wind energy. This series has been developed to further WREN's goal to create a shared global knowledge base and community of practice around research, monitoring, and management of the environmental effects of wind energy development. For each of these webinars, we will aim to provide a global perspective on some of our most pressing issues and topics of interest around the environmental effects of wind energy. If you would like more information on the International Energy Agency Task 34, or WREN, you can go to the website at www.ieawind.org or contact the operating agent, Karen Sinclair of the National Renewable Energy Laboratory, whose contact information is also on the website. The agenda for this first webinar is to have two speakers, experts in the area of bats and wind energy, that will present each for 20 minutes. We'll follow that up with Q&A, which you'll send your questions in online. We'll read them out to the speakers. I'm going to solicit some input from you on suggested topics of interest that you would like to have covered in future webinars. Our two speakers are Drs. Chris Hine, who's calling from Portland, Oregon, and Dr. Oliver Baird, who's calling from Erlangen, Germany. And we'll go right into Dr. Hine's presentation now. I'd like to give a brief bio on him first. Dr. Chris Hine is the director of the Bats and Wind Energy Program for Bat Conservation International and the program coordinator for the Bats and Wind Energy Cooperative. Dr. Hine received his master's in biology from Texas State University in 2001 and his PhD in forestry and natural resources from the University of Georgia in 2008. Dr. Hine has been studying bat behavior and ecology for 15 years and bats and wind energy issues for 7 years. Prior to working for BCI, Dr. Hine was the lead biologist for ABR, Incorporated Environmental Research and Services. Without further ado, Dr. Hine, you can begin your presentation.
Thank you. Good day, everyone. Let's start from the beginning here. So I want to begin by providing some context on why we're concerned about bats and wind energy development. So on this next slide, we see for the U.S. and Canada estimates of fatality for 2000-2011. During that time period across these two countries, it was estimated anywhere between 840,000 to almost 1.7 million bats were killed by wind turbines. And as development increases, these numbers, as you can imagine, increase as well. And in 2012, given that there was about 60,000 megawatts of wind energy development in the United States, it was estimated anywhere between almost 200,000 to 400,000 bats were killed by wind turbines. In these two countries, the vast majority of fatalities that have been recovered are from migratory tree-roosting bats. These are hoary bats, Eastern red bats, and silver-haired bats, and you can see the percentage of fatalities there. But we don't have a lot of information across many parts of the country, including the Southwest, but there is some suggestion that Brazilian free-tailed bats are also a species of concern. And in total of the 46 species in the U.S. and Canada, approximately half of these have been found underneath wind turbines. So we've looked at a couple different strategies to reduce fatality. And one that I'll begin with here on this next slide is now called operational minimization. It's had a couple different terms, curtailment, operational mitigation, but we're gonna call it operational minimization for this presentation. Next slide here, I want to go through a couple of definitions just so we're all on the same page. So for cut-in speed, this is the speed at which the generator is connected to the grid and producing electricity. Oftentimes the manufacturer's cut-in speed is between 3 and 4 meters per second. And for some turbines, the blades will spin at full or partial RPMs below this cut-in speed when no electricity is being produced. For feathering, this is adjusting the angle of the rotor blade parallel to the wind, or turning the whole unit out of the wind to slow or stop the blade rotation. The next slide. The thought process, the rationale behind this strategy came from early studies in both monitoring bat activity and fatality. So there are, at least in the U.S. and Canada, there are consistent patterns of bat fatality. Obviously, bats are only active at night, so this is, you know, half of the day that we're concerned about. We found that both peak activity and peak fatality occur in late summer and part of the fall, so a relatively narrow period time of the year. And what's key here is that the highest fatalities tend to occur on low wind nights, so that under a specific set of conditions. So we've really narrowed down both the timing and the conditions in which this strategy would operate. We also have found that bats are not killed by non-moving turbines, so it has these fatalities and this conflict here is caused by the movement of the turbine blades. And so the idea is to alter the turbine operations to reduce bat fatalities by raising the cut-in speed and feathering blades below that raised cut-in speed when bats are at the greatest risk. And so, next slide, I want to go through a couple of examples from the United States and point out some key features. So, I'm not going to be able to get into all the methodology here, but I do want to point out a couple of things. So, the first study conducted in the United States was in Mid-Atlantic in Pennsylvania. This was conducted by Arnett et al. And the study looked at 3 different cut-in speeds, the manufacturer's cut-in speed at 3.5, raised cut-in speed of 5 and 6.5 meters per second. And this study found a significant reduction in bat fatalities. Between 44 and 93% fewer bats were killed at these higher cut-in speeds. The study was not able to determine a significant difference of these 2 treatments, these higher cut-in speeds. And the other key point is that they found that anywhere between 0.3 and 1% annual power loss by raising the cut-in speed. So up to 93% fewer bats killed for an annual power loss of up to 1%. On the next slide, we see that, I know this doesn't show everything. This slide was conducted, this study was conducted in the Midwest, United States by Good et al. They used similar treatments as the previous study. The methodology was just a little bit different, but they found similar results in reduction, such that at 5.5 or 5 meters per second, I'm trying to see if I can get these slides to show up. At 5 meters per second, there was a 50% decrease in bat activity, and at 6.5 meters per second, there was a reduction of 78% in fatalities. And so this study was the first to demonstrate a difference between the cut-in speeds. On the next slide, the second year of study at this site was the first to look at just feathering the blades below the manufacturer's cut-in speed. And they found that there was a 36% reduction in bat fatalities just by feathering before the manufacturer's cut-in speed, which is of interest because the turbines aren't even generating electricity at this time. On the next slide, a study conducted in the southwestern part of the U.S. Looked at several different cut-in speeds for part of the night and all night. And this was the first study to look at operational minimization where the Brazilian free-tailed bat occurs. It's not shown on here. These last couple of slides had animations where different parts popped up at different times, so it's not showing on here. But what they found was that there was no difference between control and treatment groups at this site, and that the vast majority of fatalities were Brazilian free-tailed bats. So this suggests that operational minimization may not work in all regions and for all species. So further testing is needed in different regions. The last example that I want to go through for operational minimization incorporated another variable other than just wind speed. This study was in the northeastern part of the U.S., conducted by Martin et al., and looked at not only raising the turbine cut-in speed above the manufacturers, but also incorporating temperature such that the implementation of this wouldn't occur unless the temperatures were above 9.5 degrees Celsius. And they found a 60% reduction in bat fatalities. So there are ways that we can, other variables that we might be able to include to refine this strategy and maximize wind production and minimize fatalities. On the next slide, as we move forward, one is, at a minimum, operators should be feathering up to the manufacturer's cut-in speed. There's no loss of production. There's no loss of the energy generated, and bats are being killed. And early evidence shows that we can save roughly, on average, 30–35% of the fatalities. And as we try to refine the strategy, we can incorporate additional weather variables such as temperature, maybe barometric pressure, to reduce the changes that are needed to be made. And of course, we need to test this in different regions and different species to see how effective it might be. So the ultimate goal is to create an automated turbine system that regulates itself through the SCADA system to incorporate changes based on date, time of day, wind speed, temperature, and other variables that are that prove important. On this next slide, we know that operational minimization is not going to work in every situation. There are certainly costs that are associated with changing turbine operations. These costs are relatively unknown and are going to vary from location to location. There's also some concern that changing these operations and having the turbines do things that they're not normally designed to do could cause some impact to the turbines, and this needs to be investigated. From the conservation side, this strategy is not going to work in low wind regions where the facility is generating the vast majority of their electricity in under low wind conditions. It's not likely that they're going to raise the cut-in speed and lose out on the most important period of or conditions that they're producing electricity. And it may not meet all of our conservation goals for all species. As I said earlier, this needs to be tested in a number of different regions to see if it works for all the different species of bats we have here in the U.S. and elsewhere. So it's important that we come up with other tools or other strategies that are an alternative to operational minimization that would benefit all involved, all the different stakeholders. Next slide. And this, one of these strategies is to use ultrasonic deterrents, or at least to test these devices to see if they indeed work. Next slide. The idea behind using ultrasonic acoustic deterrents is to essentially jam that sonar, interfere with their ability to receive their echolocations, make an uncomfortable airspace in and around the rotor swept area. Ideally, once these are tested and And if proven effective, the cost would be predictable. You buy the equipment and install it. There would likely be occasional maintenance fees for the devices, but it's something that you could plan for. At this time, there's only one published study using acoustic deterrents, so it's unproven. And there's the challenge of broadcasting sound out to any great distance, particularly high-frequency sound, which attenuates in the atmosphere rather quickly. So one of the challenges that we face with this particular strategy. Next slide. So the Bats and Wind Energy Cooperative has pursued this strategy since 2006, and at that time, prior to even considering putting these devices up on turbines, we looked at a number of lab and preliminary field tests where we tested these devices indoors in a lab setting and on the ground, looking at reduction in bat activity when these devices were turned on. The first ever study using these devices on wind turbines was in 2009-2010 at a site in Pennsylvania. That data was published by Arnett et al. In 2012. Last year at this time, in August, we organized a technical workshop to examine the next steps, where we needed to go, how we needed to improve the devices. And in October, we tested a slightly modified device on the Hawaiian hoary bat, looking at how deterrent technology might affect their activity. It's an endangered species, and as wind energy development continues on the island, there's some concern for that bat. And right now we're in the process of modifying the device and testing the next generation device. The next slide shows some of the specifications for the deterrent device. It's a SenseComp 600 environmental grade electrostatic transducer. It's rather loud within a short distance, 122 decibel levels at 1 meter. This is about as loud as a rock concert or jet engine. And the frequency range initially was between 20 and 100 kilohertz that we used for the study in Pennsylvania, because this encompassed all of the echolocation calls from the different species in that region. But this can be programmed into the deterrent to match whatever your conditions are. During this study, we used 8 devices per turbine, and we selected 15 control turbines and 10 deterrent-equipped turbines. These treatment groups, the control and the deterrent turbines, were fixed, so they weren't rotated on a nightly basis. And in 2009, we conducted the study. In 2010, we did we assessed whether there was any inherent variation between the control and treatment turbines. This was done prior to the official testing, so in a different time of the year. We did find a inherent variation between these two sets of turbines. Though it was insignificant, we decided to apply that to the analysis in order to be conservative. And I'll get into that in just a few minutes. So this next slide shows a rough schematic of how the deterrents were placed and oriented on the turbines. As you can see, we had 3 on each side pointing down, and then 2 on top of the nacelle directed toward the blade and away from the blade. We found in the first year 21 to 51% fewer fatalities at the deterrent-equipped turbines, and a significant difference in fatalities. The next slide, showing the 2010 data, showed very similar results. We found an 18 to 62% reduction in fatalities. However, when we applied that 9% inherent difference, the results varied even more, such that it suggested anywhere between 2% more fatalities to 64% fewer fatalities occurred at deterrent turbines. This next slide shows some of the specific, species-specific effects. And what was encouraging here is that it tended to work very well for low-frequency calling species. In this case, hoary bats and silver-haired bats, which both call at or below 30 kilohertz. And in both years, the hoary bat showed a significant reduction in fatalities at deterrent turbines, and in the second year, the same for silver-haired bats. So this might suggest that for the Brazilian free-tailed bat, which operational minimization may not work for that species, that acoustic deterrents might, because it is also a low-frequency calling species. And the deterrent may work better for these types of bats that use lower frequencies, because the sound of the deterrent travels farther, and these bats may be picking up that noise and being deterred from the area faster than higher frequency calling species. The next slide. So what we're trying to do now is improve the device. We experienced a number of malfunctions and weather issues with the first generation device. And so we've spent a lot of time trying to make the deterrent more robust and more weather-proof. The other thing that we need to explore is optimal placement and orientation. This was one study with one set of deterrent placement on the nacelle, but as we learn more about how bats are interacting with turbines, we might be able to optimize where we place and orient these devices. And then finally, what we're testing is different frequency patterns, not just a constant broadband noise, but frequency sweeps going from high to low or low to high, or patterns of transmission. So there's a randomization of pulses that are emitted from these deterrent devices, which may further confuse bats as they're trying to navigate in the area. This next slide shows the comparison between the two strategies and our understanding of these at this point. For operational minimization, we have a number of studies to inform us on its effectiveness, and it does appear to be effective for certain species. We still need to assess what the impacts to the turbines are over the long term. There might be some difficulty in implementing this strategy for existing facilities because the facility already has a power purchasing agreement in place. But for new facilities, this can certainly be factored in. For specific species, again, it worked very well for the migratory tree-roosting bats. It might work well for myotis species because they're smaller-bodied bats and are more active at lower wind speeds. But for the Brazilian free-tailed bat, it's at least at this point, it doesn't appear to be effective. And where we need to go as we move forward, I think that feathering should be implemented up to the manufacturer's cut-in speed as a minimum, and then pursue efforts to refine the strategy such that it becomes more universal, more accepted by the industry, and we can achieve conservation value for bats while still producing energy. With respect for acoustic deterrents, at this point there's only one published study. The results were not ideal because it suggested that potential 2 to more fatalities could occur. But again, that inherent variation that we added was insignificant and was tested during a different time of year. So I really think that this is a conservative range for the effectiveness of this deterrent. The maintenance costs are still unknown over the long term. Again, we're trying to improve the weatherproofing of this device. The cost in this case would be upfront, and the effects for species, it appears to be more effective for lower frequency calling species, but certainly more information is needed to determine this. It did work very well for the Hawaiian hoary bat in deterring them from their foraging areas. And then, we're still in the process of research and development on this technology in general, and how we can improve it through transmission patterns and frequencies and placement and orientation on the turbines is still, we still need to look into that. The last slide here, I think the goal is for everyone, to minimize bat fatalities and maximize wind generation. And so both of these are still kind of in their infancy on how we can improve and refine these strategies. We need better information on the relationships of fatalities with weather conditions so that we can refine. We need to learn more about how bats are interacting with these turbines. Video evidence using thermal imagery has indicated that the vast majority of passes of bats are coming from the leeward side of the turbine, kind of from the back side. And so this might indicate where we could focus our deterrent technology and broadcast those signals to optimize that technology. We also need to integrate these strategies with the turbines. They need to be part of the package. So as you're negotiating with turbine manufacturers warranties, having dedicated space in the turbines, being able to mount these devices on the turbines without voiding the warranty will be important. And then adapting the SCADA system such that they can incorporate multiple variables, not just temperature, or not just wind speed, but maybe temperature, barometric pressure, humidity, whatever the case may be, will be important so that the changes made to the turbines are as minimal as possible. With that, I want to thank NREL and the Task 34 for giving me the chance to present today, and I want to thank all of our partners through the Bats and Wind Energy Cooperative in conducting these studies. Thank you.
Thank you, Dr. Hine. We're going to move over to Dr. Oliver Baird's presentation, who, as I mentioned earlier, is calling from Erlangen, Germany. Also, a reminder to the group on the line that you can send questions at any time. If we don't get to Q&A after the presentations, we will make sure to distribute responses to you via email and/or on the IEA Wind Task 34 website. A little bit about Dr. Baird. He received his master's in zoology in 2001 and has his PhD in biology from 2005 from the University of Erlangen, Germany. Since 2005, Dr. Baird has worked on environmental impact studies and data analysis for several wind energy projects. Between 2006 and 2009, Dr. Baird served as the project director for the development of methods to analyze and mitigate collision risks of bats at onshore wind turbines, a project funded by the German Ministry for Environment, Nature Conservation, and Nuclear Safety. Since 2011, Dr. Baird has worked on 2 follow-up projects funded by the same ministry. Over to you, Dr. Baird.
Yeah, thank you for the introduction. I'm going to try to highlight the European perspective on mitigation, and I'm going to present data mainly from the project that I have been personally involved with that were mentioned in the introduction. And I'm also going to give a quick view on other systems currently used in Europe. Amongst our co-workers, our partners in our project, I want to mention Enercon, a large manufacturer of wind turbines in Germany that has been working with us on all these projects. Next slide, please. Yeah, can I see this video? Or maybe I can do it myself. Yeah, this is a stereo infrared imaging we did of bats at wind turbines, and this bat is being hit by the rotor blade. I'm going to replay this. So bats are being affected by wind turbines, and this is unfortunate for the bats themselves, of course. but also now back to the presentation. But in Europe, it's also a large problem for the next slide, please. A large problem for developers, because all European bat species are strictly protected within the EU by European laws and also by national and partly by state regulations. So possible impacts on that have to be studied and considered during the planning process. And in Germany, this has led to the situation that for some sites, permission has been denied altogether, or operation of turbines was heavily restricted. However, the methods to estimate and deal with bat collisions were not standardized when we started our work, and so there remains a large body of uncertainty during the permission process for the governmental agencies, but mainly for developers and also for the investors. Next slide, please. So we were looking for a standardized method to estimate the number of bats being killed at a specific turbine, to predict times of high mortality risk, and in the next step to mitigate the impact on bats. And we did this by stopping or feathering the rotors during times of high mortality risk. And I'm also going to show some data on an experimental validation of these mechanisms, of the operational algorithms we are using or proposing. We gathered data mainly by two methods, by fatality searches, just looking for dead bats below the turbine, and by acoustic monitoring of bat activity. Bats use ultrasound to orientate, and you can use automatic detectors to record these calls. Next slide, please. Why were we using acoustics? I want to highlight some points on that. Because fatality searches are expensive, and in Central Europe they are usually not performed with adequate search intervals because it's costly to search many times. Also in Europe, many studies do not account for search biases, which are, for example, the fact that you can't search the entire area below the turbine, and this area may vary during the year. Bats are being removed from the area by scavengers. For example, here a beetle removing or burying a dead bat in the ground, or foxes eating dead bats. And also human searchers can't find all the dead bats actually present below the turbines, even on a gravel field like this. So we did some calculations and built a model, and for example, if less than 40% inside a radius of 50 meters around the turbine can be searched, and at the same time the scavenging rate is intermediate or even high, it is not possible to come up with a reasonable estimate of the actual fatality rate. So at many sites, at least in Central Europe, fatality searches yield little information on bat fatalities, and so we looked for a different method and used acoustics for that. We collected data in a pilot study in 2007, and then our main data set was from 2008 in our first study at 70 turbines. We installed detectors at the nacelle. Here a picture of the microphone position in the ground of the nacelle. This is the microphone view towards the ground, and these are the detectors we used, the Anavet and the Baird, and now we're also using the Avisoft system, and this is what our setup looks like in the nacelle. So what we can measure when we look at bat fatalities at turbines is when we do fatality searches, the number of fatalities we actually find. Then we can measure the scavenging rate, the fraction of the area searched, and the search efficiency. And the usual approach is then to use these figures and one of the formulas available to calculate the actual number of bats being killed. And we also included information on acoustic activity and on wind speed to come up with a more exact, with a better estimation of bat fatalities. And the advantage of this model is that once the model is established, you can use only acoustic recordings and wind speed to predict the number of bat fatalities. And this is the core finding of our first study, we see fatality rates from 0 white to almost half a bed per night in red, and fatality rate increases with acoustic activity from left to right, and we see that the most dangerous wind speeds are around 3 to 5 meters per second. And the black dots are the nights we actually sampled. So we came up with numbers, mean numbers for bad fatalities, 6 from fatality data, fatality searches only, and then including the acoustic data, we had a little bit, a number a little bit less than that, with 5 beds for a 3-month period in the summer, and we estimate that the actual fatality rate during the entire year is about twice as high, so 10 to 12 beds per year killed as a mean number at the sites we sampled in Germany. So we have now a system to estimate bad fatalities, and the next step is to look at when these fatalities occur. And as Chris presented before, wind speed is a good predictor of fatalities and of bad activity at wind turbines. And here you can see our figures with bad activity on the y-axis decreasing sharply with higher wind speeds and almost no bad activity left at more than 6 meters per second. And I want to say at this point that this is for the species in Central Europe, and for example, free-tailed bat species may be a different issue because they will be flying at higher wind speeds, so this correlation will be different for these species. But for Central Europe, this works well, and also for different species and species groups, which are given here in different colors. For each one of them, activity decreases sharply with higher wind speeds. Different people have already in the past, these are only the first studies, Chris showed several more, to use this to reduce bad fatalities at wind turbines and to raise the cut in wind speed and so avoid bats to collide with the rotor blades. We did the same thing based on our big data set from 70 turbines. So we want to differentiate between situations when bats may be active in the rotor swept area of a wind turbine here on the left-hand side, and situations when bats would rather stay in the roost on the right-hand side, or at least not be active in the rotor swept area. And we used wind speed as a predictor for these situations. We also included night time and month to predict times of collision risk. We also tried precipitation and temperature, but in the end we left them out of the model again because they didn't increase the results substantially, but they will increase the cost of measuring and implementing the algorithms. So that's why we didn't use these variables. We feed this model into the computer running the turbine, and then the computer will shut down the turbine at times of higher collision risk. This was the result from our first study, and in our second study we validated these algorithms we had developed. We did this in 2012 in a field experiment at 16 turbines at 8 sites. These turbines were sampled before, so we knew we had data on the acoustic activity at these turbines. We performed acoustic recordings and daily fatality searches during 3 months in the summer of 2012. We set up the experiment in a way that we had 2 turbines per site, as in this picture, and one of these turbines would be running with the mitigation algorithm, the one in the background in this case, and the other turbine would be running normally. And then after 1 week, we would switch the regime, and the other turbine would be running with with an increased wind speed. And we went on during the entire time of the experiment with these weekly intervals. Our aim was to reduce the fatality rate from 12 to 2 bats per year. So we would expect a ratio of 6 dead bats to 1 for turbines in normal operation or in bat-friendly operational mode. This is what one day would look like in this experiment. In black you can see the wind speed, rather low during the first half of the day, a bit higher during the second half. In red you can see the mitigation cut-in wind speed defined by our algorithms, only for the night of course, because bats don't fly during the day. And in green you can see the rotation speed of the turbine, and when the rotation speed is higher than 4 rotations per minute, the turbine is running normally. So during the first half of the day, the second half of that night, wind speed was rather low and below the cut-in wind speed defined by our algorithms, so the turbine was not running. During the day it would run normally, and then in the evening the wind speed was higher, and except for one time slot at around 9 p.m. the turbine would be running normally. And the black dots are recordings of bat activity, of acoustic bat activity. In this sample, the acoustic activity was within the times where the rotor was stopped to avoid collisions with the turbine. What did we find? We found 23 fresh bats, so these are bats that were killed during the previous night, and with a ratio of 6 to 1, as I had mentioned before, we would expect around 2 to 3 dead bats for the turbines running with curtailment, and a little bit more than 20 dead bats for the turbines running without curtailment. And what we found was a ratio of 1 to 6.2, so our actual results were very close to the numbers, to the figures we had expected. And there was a statistically a significant difference between turbines running with and without curtailment. And when we extrapolate these figures for the entire year, we come up with numbers of around 1.9 dead bats for the turbines with curtailment, and a little bit less than 12 dead bats for the turbines without curtailment. The question then is, of course, what will this cost? And I'm sorry, I still can't present final figures for this because it's been very difficult to get the figures from the developers or from the investors. I think we will have them collected by the end of the year and then have the final figures. Up to now, we can only calculate the loss as a percentage of a presumed yearly revenue of 4,500 megawatts per year. And we predicted from our 2008 data set a maximum of around 1.5% of loss of yearly revenue, a mean of around 0.8%. And what we measured in 2012 was a maximum of 1.8 and a mean of around 1%, so the figures are a bit higher. However, I have to mention that this is not a random sample because we used the turbines with high fatality numbers for our experiment. So curtailment losses would be a little bit higher in these turbines too than they would be in a mean or in a random sample. What do we do with our method, or what do the governmental agencies do? And this is an overview of different regulations. The one we have for the entire EU, which is only a recommendation by the EU Commission, and then the different federal states in Germany. They all have their own regulations. And in red here highlighted, you can see which ones of these regulations include mitigation algorithms, and you can see that by now in 2014 the majority of these regulations include mitigation algorithms as a method to compensate or to reduce bat fatalities, and most of these regulations refer to the method we developed. So I think we're on the way of establishing a standard method of mitigation in Germany. At this point, I want to look at different countries in Europe. We have two similar systems right now, or two systems I know of, one in France by a company called Biotop, they call it Curatech. The idea is similar to what Chris showed before, or of what I have shown of our work. Rotors are stopped during times of high collision risk. The difference of this French system to ours, or there are three main differences. One is that they are not able to actually calculate fatality numbers from acoustic data because they don't have a reference data set as we have. The other difference is that they try to include online data, so like camera data or acoustic data to stop turbines when actually a bat is, or a bird also is recorded in the wind park. And the third difference is that this is a private company, so it's not so easy to get information on the system, and because it's not published, they sell it as a black box, more or less. This is also true for another system that has been developed in Spain, DT Baird. It's mainly used for birds and for large birds, actually, for vultures and for cranes, for example. Cranes during migration. And this system also uses cameras to detect birds or possibly also bats and to shut down turbines when animals are in an area where they're endangered by the rotors. This is also a private company, so it's hard to get more information than the one you will find on their website. Next, I want to talk about some technical aspects of acoustic sampling of bats at wind turbines and on the software analysis. We developed a new detector system in cooperation with Avisoft to record bats at wind turbines. This will be out next year, and it has a rather good resistance to ultrasonic noise and low maintenance requirements. And special features that are important when you're working at wind turbines is remote access by Wi-Fi or by mobile phone net to see if the detectors are running. We have an improved microphone disc with a heating. This is a picture of the heated microphone disc to reduce the impact of humidity of rain. And it's basically a computer in that black box you can see here. And we have a sophisticated software running on it, so it has a high sensitivity for bat calls and hence an increased detection range compared to other detector systems. This is a new development compared to the ones I had shown you before that we used in our first sampling in 2007. I'm going to skip this because we don't have that much time. Then I want to talk about the software we developed. It's only in German up to now, unfortunately. This is a screenshot where you have to type in information on the site you've been working at. We published this software in 2014 at our website. And what it does is it's based on Microsoft Access runtime, and it's free of cost. It calculates the expected number of fatalities per year based on acoustic data and on wind speed data. And it also calculates what we call bat-friendly operational algorithms for a number of bat fatalities defined by the user. Up to now, it only works with bat color data, but we want to extend that until next year for ANABAT and Avisoft acoustic data also. And this is just what the report looks like of the program. On the right-hand side, you can see the mitigation algorithm with the cut-in wind speed specified for the month and for the nighttime. And as last point, I want to talk a little bit of what we're going to do, or what we're currently doing in our third research project. And I'm only going to talk about the main point, which is highlighted here, which is the question of the necessary sample size to measure bat activity. and we're looking at temporal variability and within inside spatial variability. So the first question is, how much does bad activity vary between years? We have very little information on that so far, and usually turbines are sampled for 1 or 2 years, and then they're running for the subsequent 20 years, and nobody will look at what the bad activity is like at these years, at these 20 years. So we are looking at the variability between years and also between seasons. We do acoustic sampling, and we are resampling 16 turbines at 8 sites. We have already sampled in 2008 and 12. Hope to get some information on temporal variability on that. And then we'll also, next year, we'll look at spatial variability. We'll sample 32 turbines for that. And we want to look at the variability of bad activity within one site. And the main question behind it is, how many turbines do I have to sample to assess the site? Do I have to sample all the turbines at one site, which would be rather a long case? Is it enough to sample half of the turbines or just a small subsample? Presentation is not moving on. Yeah, just a small subsample. Or is it even enough to sample just one turbine? This is what we want to look at next year. And the last question I want to show here is the effect of the rotor diameter on fatality numbers. Until now, we extrapolate the fatality numbers for large turbines based on the spatial distributions of beds in the rotor swept area. And we are going to sample large turbines with a rotor diameter larger than 80 meters in the next year to get a correlation of acoustic data and bed fatality data. So a quick summary of the results I've been showing is we found a model that predicts collision rate from acoustic data and from wind speed data. We developed bed-friendly operational algorithms, and they seem to work properly when we look at the data that we've gathered so far. Bed-friendly operational algorithms are becoming a standard method in Germany, and in the other 2 countries that are doing some research on this topic, in France and Spain, they're also working in a similar direction to mitigate fatalities. And currently hardware and software tools are being developed or refined to meet the needs for this task, to measure bed activity at the turbines and to reduce fatality numbers. Yeah, finally I want to thank the ministry that has funded our research, and our co-workers and colleagues, and you for your attention. Thank you very much.
Thank you very much, Dr. Baird, and thank you, Dr. Hein, for your presentations today, and thanks to all the attendees of this first webinar of an ongoing quarterly webinar series. We'll conclude. We ran out of time. We'll conclude this call at this time, but we'll keep the webinar open for a bit longer, collect any additional questions you may have, any ideas for future webinar topics. We'll keep the webinar open for a bit longer, or you can send them over via email. We'll disseminate answers to questions via the webinar and or via email. Thank you very much.